model to data so that we'll be able to henceforth use our model without having to wait for our data collection to make decision. And you saw that yesterday when we are done doing our parameter estimation, it was possible for us to determine each of the equations explicitly. Explicitly in the sense that you now have an equation that the parameters are not just unknown parameters any longer. Is that okay? They are not unknown parameters. So, and for people who are doing something in statistics, you know that sometimes you have some covariates, right? Are we together? And you want to determine a certain outcome given the covariates. So the idea has always been that, okay, with this our covariates and this outcome variable, can we see a relationship? Can we see a relationship? Can we get a function to capture that relationship so that we'll be able to now determine for people. I think I was discussing with somebody yesterday, and then he was talking to me about drug acceptability, right? I was saying there are various things that are implicated, various factors that you can bring in as covariates. And so the idea is that these outputs that we want to determine, once we know the covariate, can we always determine it? And so that will be possible when you have calibrated your model, so that, you know, henceforth, for instance, what we did yesterday, having determined explicitly the values of A and B in this case, the values of A and B in this case, the other variable which is in the dependent variable X. Now, if you now know dependent variable X, you can know what independent variable Y. Once you know independent variable X, right? You can always know what independent variable, dependent variable Y will be, isn't it? Because you already know A and B. Are we together? A and B are already determined. So, if, for instance, like I said, you are looking at you are looking at temperature, like Mr. Sam taught us, and then you are looking at a certain response. Maybe, for instance, you have expressed biting rates in terms of temperature, where temperature is X in that case. Once you have determined the A and the B, the temperature, I can determine what biting rate I'm expecting, right? Are we together? Now, the other one that I sent to us, I think I sent 3 data yesterday. I've sent another one this morning. Did you see it? Because you don't check your WhatsApp. Oh. It's there now. No, there has been network. Let's just check. People have sent it since now. Yes, flu. You see, flu.csv. Yes, so we are going to be using that one this morning. But this is the third example we're supposed to consider for the third data sent yesterday. But I would want you to do it by yourself. This time around, I'm providing you the function. This is the function we want to fit. And you have the data already. So this will be an assignment for you because I will not do it here. Yes, you would do it by yourself. So you want to determine K, R, and X naught. Is that okay? You want to determine K, R, and X naught. So we want to estimate those parameters. And our variables are Y and what? And X. So the data contains y and x variables. So, but from there we want to determine k, r, and x naught from that, from the estimation process. So I will not go through this one since you already have the function with you there. So you should now begin to engage yourself in rigorous thinking. How do I go around this? It's the same process. You have the function already. Of course, I will flip through it so that you see the same process, right? I should not send the code. I want you to click yourself. All right, so I want you to do it yourself. No, I actually am not intending you to see the code. I'm not intending that you see the code. The question is what I want you to see. So you have the data, right? You have the data with you. Data 3 sent to you yesterday, right? Plot the data, visualize the data. You will see that the data is like something showing a kind of exponential growth and then later stabilizes afterwards. So, and for that, I've told you that the process is you observe your data, you look at the pattern in data, and then the pattern in data tells you, okay, what kind of function will fit this one? So because, like I said, that data you see when you lay your hands on it, you know, you have something like an exponential growth that finally now stabilizes somewhere. So we thought that logistic growth rates can handle that. Logistic equation can handle that. So, and that's why we have suggested that. But of course, what is necessary for you to do now, two things that you need in your hands to do this are the data and the model. Once you have the data in your hand, you have the model in your hand as well. You can do that one. So on curve fitting, I am giving you this one to do personally. So you have the model here already, so and then you have the data. All right. So you will do that and give whatever the answer is. So you are supposed to get something like this when you are done fitting, right? I've given the equation again and again. I've given the equation and again. Look at it. Logistic equation. Can you see it? Y equals to. It's there already now. I think I deliberately left this. Okay. I see. Can you see it now? Okay. So that's the logistic equation that you are going to fit to the data 3 that was sent to you. Every one of us, we have access to the data already. I have carried out 2 examples. I want you to use the same process that we used in the example to try this one. Don't worry. It's not all going to be smooth. No, you don't snap the code. I don't want you to see the code. If you snap the code, then I'm not giving you assignments. No, don't snap the code. That's why I'm fast moving it from that place. Since you have seen one code already that I've done nonlinear equation already yesterday. So it's that same process that you will use. The same process used yesterday. So if you don't try something and hit the wall, and then you try to see how do I navigate the way, you won't get to build your capacity. if I have to give you everything and then you think, wow, I know it. No, you don't know it until you try it. So try it. All right, thank you. Let's move on. So like I told you, you are supposed to have something of this nature. Now, quickly, we move on to compartmental deterministic model fitting. Now, this is important for me because now the difference between this kind of model and the one that we did yesterday, I've told us the one we did yesterday, what kind of model did I call it yesterday? If you can remember, the one we did yesterday is statistical model is statistical model. But I said statistical model are functional models, right? They are functional models. They are not concerned with the dynamics, the internal working of the system. They are not concerned with it. All we are concerned with is we have inputs, we have outputs, we plot the resulting graph, we see the way it's going, we think of, okay, what function can best represent this? That is statistics for you. But here now in mathematical model is not just thinking functional, it's rather thinking systemic. Say this is a system. If I have malaria cases, flu cases, malaria model is not just, mathematical model is not just thinking that, okay, this is malaria cases against time, and then it will plot its cases on the y-axis, then on the x-axis we have the time, and then we are seeing the way the plot is going, and then we now want to look for a function which will be a function of time. No, it's not thinking that. Mathematical models come from the idea that these cases that I am seeing came from a system, right? And there are different things, there are different factors that work together to produce this, and it's interested in tracing that, not just saying this is the input, this is the output. It's interested in tracing that one, the process. Are we together? So we call it process-based models. Are we together? So in that case, now, so please, I want you to bring this flu data. Just read it in, as I taught yesterday on how to read in data. Don't forget, you have to use the path where your data is, your own data is. So this is my own path. So you trace your own path and bring in the data into our environment for use. That we have been talking about and we have been doing, and the functional now. For the functional, if I want somebody, while the rest, every other person is typing, I want somebody to tell me if it is functional. Once you bring in your data, what is the next thing that I want us to see? Observe it. How do you observe it? You view. How do you view it? You plot it, right? You plot in order to visualize. Okay. When you visualize, what should have been the next step if it was statistical or functional model? Once you view your data, what should be the next step? You think of the time. No, you have plotted it now. You think of what? The type of function, isn't it, that can fit, right? Now, but this one we are not going to do like that. All we are going to think about now is we are going to think about flu. We are not just thinking about x and y axis. We are not just thinking about cases against time. No, we will think flu. This is flu coming from. You don't have what? But I sent it to the platform. Please, can you help us with network? Or one other thing, if you have gotten it, you can transfer it to another person by your side. You can use cable now. Send it either to your phone with cable and help transfer, or you use Bluetooth. Those that have got it, a lot of people have gotten it and they are working with it already. So you can use Bluetooth to transfer to another person if you have not gotten it. The data has been sent since, so I expected I would have downloaded it. So please help your neighbor. Help your neighbor. Use Bluetooth to send to your neighbor. For those of us that already accessed it, Bluetooth does not use internet. So at least we have. Are we helping ourselves already? Okay, thank you. Now, just like some of us said that the network is not so good, even if I send a code now, you will still tell me that the network is not good. So it's the same thing. When I send, the network will be good. But when to read in the data, the network will be bad. Okay. What do you have? You must have error. It's correct. Thank you. Thank you. Thank you. I'm happy to hear that. By now, having spent this number of days working on R, you know that when your own is not working, there is a problem. And then you have to read the error message. Not mind if they are seeing, if they are doing it already. I should not mind if they are doing it or not. Not mind if they are doing it or not. All right, so we move. So you can check the summary of your cases just to see the minimum, the maximum, the first quarter, the second quarter of that data. You know, once you type summary, you will see that one. Now, for flu, what kind of force of infection is this? It's what? What is mass? Mass what? Mass action, right? Why are we thinking mass action? Why are we thinking mass action? One is for a small population. Not only that, even the disease itself. Is that okay? The disease itself, the mechanism of flu spread is that it spreads where people are closely, where we have dense population, right? For instance, now, if we are 20 in this place now in each compartment, look at it. Let's say in this compartment, we are 200 seated, right? And one person has flu. How fast will it spread? Compared to if you have just 5 in the entirety of this hall, and every person is just seated in each of the compartments. Which one will spread faster? The 200, right? Because people are closely, compacted, right? So it will spread faster in that case. Do you get? And then again, the population is still now. So basically, the disease mechanism of spread, agrees with density-dependent situation. Is that okay? All right. Now, if you look at the data as well, you will notice that we just have about 14 data points. Do you observe that? It's a very short outbreak. Very short outbreak. So should we be talking about endemic situation? Should we talk endemic situation here? We should not. because we are not expecting that somebody, no birth and death situation will happen. Do you understand? It's a very short outbreak, so we don't have to cater for. So this is what we have been talking about, and you already know this equation already. So, and we also know that people recover, is that okay, from flu, and within that short day, we are not thinking that somebody also goes back to being susceptible or something. Is that okay? Because it's a short outbreak. Now you see now that approaching this now, I have not even thought about my x or y axis of the data. I am thinking the model, I'm thinking the disease, right? Are we together? The first thing I'm doing is I'm thinking the disease. The first thing a statistician does when he sees the data is that he thinks the data, right? When a mathematician gets the data, he does not first think the data. He will think the data, but he thinks of the process that produced the data. Are we together? Because it's about disease outbreak. So he thinks about that process and wants to produce that process. So the process is hereby produced. Are we together? All right. So next thing here is that, okay, we have to write R code to implement the model. I taught you this already. This is another way of doing this, where you put your closed SIR model and then function. Now, I've told you that you can always create your own function, isn't it? You can create your customized function. If you build model, it's a customized function. Is that not? Are we together? It's your own function. You are the one that builds the model. All right. So in that case, you must know how to bring whatever function you create by yourself into R. How do you bring it into R? You assign it a name. In this case now, I've assigned a name, close.sir model. Right? I've assigned this name, and then I want to define the function. It's the same thing we do in mathematics, where we say f of x equals to x squared plus 2 or plus 1. Is that okay? When you say f of x equals to x squared plus 1, what are we saying? We are saying f is a function of x. Do you understand? In our case now, for our deterministic model, what do you think our model is a function of? It's a function of time. It's a function of the parameters and the function of what? The state variables. So we have to just write. So we are saying that close.sr is a function of time. X there means the state variable, right? And then params means the parameter. And then we are now saying that we want to now define what that function is. So when we say function of x equals to, so we want to define what that function is now. So, and then to define the function, we know that we have variables that are SIR in the model, right? Are we together? So x that you are seeing there under the function is the vector that houses all the variables. Is standing for the state variable. So when I'm to express x, I will have it as what? Set. I will have it as, I will write as a set, right? S, I, and what? R. So it's a vector containing three things. Do you understand? So I need to declare that the first component is what? S. The second component is what? I. The third component is what? R. Is that okay? For params too, it's also one thing that is housing different parameters that are in the model. What are the parameters in the model that we saw? Beta and what? And gamma. So you do beta. So that's why, and then we are specifying beta, the first component, and the second component, like that. And then we now build the model itself. The S is what? Beta minus beta S times I. Then di minus then beta Si minus gamma, and then the rest. And then you say list. So whatever your last line of code is under function is what will be executed. Are we together? Whatever your last line of code is what will be executed. So that means you are asking it to list. This is what the final outcome will be. It's supposed to do. So you have, having done this, if you have typed this, that means you have been able to implement your model in R. You have put your model into R. Right? Is that okay? So no matter how complex the model you are working with is, you follow the same approach. However, you will notice that in typing this, I use SIR to bring out each of the components, but this can be a long situation in some cases, right? Imagine you are having the variables to be like 10, 20. You are having the parameters to be like 30. So that means you have to be writing a long line of code. So for you not to do that is the reason why we did what we did yesterday, where we use with and then you put as dot list, isn't it? And then you now put C and you put your params and you put your X or state, as the case may be. So either you use that way or you use this way, but know that this one will always give you a long line of code, right? This type will always be longer than the other one. That one is shorter. Okay, but I just, so that when you see this kind of code another time, you won't say that, but they didn't teach us how to write like this. So you can also write like this. Now, a rule of thumb, I will not go through this so much. Now, even though you want to do model fitting, the first thing to do is that you should always try to simulate, the model using preset parameter values. The reason is that, when you are, this is a biological system, right? This is a biological system. You are talking about humans. So you should not have a situation where your solution for the S, I, and R, you are having negative. Is that okay? You should not have. That's why for mathematicians, they prove positivity of solution as one very important thing they must do, because you are talking about biological system. You cannot say you are having minus 20 human being. Right? You can't be talking like that. So run a simulation, simulate first this model just to see your outcome, to be sure that your outcome is not giving you weird results. Is that okay? All right. So I did this one already yesterday, so necessarily I will not have to stay long on this. So at this point now, like I told, okay, you always need D sub in order to be able to use the numerical solution, the numerical approach of solution in this work. And then now you specify your T sequence 1 to 14. Anyway, sequence helps us to generate numbers based on the number of steps that we indicate. So where you have sequence, that means start from 1, end at where? 14. Is that okay? When I don't specify the step or the step, that means it's going to take 1 as the default. The default is what? 1. So that means it will go from 1, 2, 3 up to what? 14. So it will generate 1 to 14. So if you run that now, if you run T, you realize that, and you call out T, you get 1 to 14. All right, and I put beta there. This one now, I'm not talking about fitting yet. I just was thinking of seeing my outcome to be sure that it's not weird. I'm not having negative results first and foremost. So okay, maybe I should also write. So then you can view your outcome by saying view out. You view the data frame or plot the model solution against time to confirm there is no negative solution or non-numeric outcomes. You should not be having NA. Is that okay? As your outcome. So when you have ascertained that, and note that if you want to simulate, this would have been the end. This would have been the end of it, right? However, what we did was just to ascertain that the model behaves well, in the sense that we are not having weird answers. So now what we do is to move to the model fitting process now. Okay, so we will be coming up with the R code to link the model and the data, and what we use to do that is what we call error function. What do I call it? Error function. I told you last time that there are different ways, there are different methods, and one of them is LSE, the least square estimation, right? Are we together? The least square estimation. What does this want to do? The least square estimation tries to minimize the sum of square error between model and data. Are we together? Are we together? It tries to do what? Minimize the sum of square error between the model and the data. That's what LSE method does. Okay? So to come up with that function that will bring data. Now, if I say I'm trying to reduce the sum of square error between the model and the data, meaning that I will have to look at the difference between whatever my model outcome is giving and the data is. How do you find the difference? How do you find difference? Model minus data or data minus model, either of the two, right? But I said sum of square error, so I will have to take the square of it. Are we together? I will have to take the square of the difference. And then, you know, because we have the data span across time, so we take those squares and then we sum it up. So what this algorithm is about doing for us is that it's going to minimize that error. And so in order to do that, so we have defined a function as a function params O or param 0 and data, right? Yes, param 0 because parameters, we are to estimate some parameters here. Data because we want to bring in the data that we need. So here, I am saying again that my t, right? My t is what? Data, right? Now, one thing that we have not been able to mention, if I can get marker, I will appreciate it. Here is that when you have data, you can, I told you can get columns, right? You can get columns, isn't it? Of data by using $sign. You can also get it by using this square bracket. For instance, I have saved that data that I sent you as data. Is that okay? If I have saved it as data and I have this, if I have x comma y, that means I'm talking. Please, can you show the board so that everybody can see it at once? So if I do this, that means I am talking about a data point. I'm talking about a point in this data. I'm talking about a point in this data such that this is the row and this is the what? Column, right? But if I now put data, sorry. Can I get another marker? So, but if I do this, for instance, that means I'm saying that across all the rows, give me column y, right? Because I didn't specify any row. So it means across all the rows. Do we get that? Do we get that? And if I do this as well, that means I'm saying across all the columns, right? Give me row x. Do you understand that now? Is that okay? So there are two ways I can get columns from data. I can say like data and then do $sign y, or I just say data, right? And then I don't put anything in the row and then colon, I say data. So it will give me colon y. So if, for instance, I'm looking for colon 2, so it just give me colon 2, right? Are we together? Is that okay? Or I can specify the name of the colon. Sorry, if I have to specify the name of the colon, I must put it in quotes. All right. So in this case now, that means I am saying that data T here is to get colon 1, isn't it? All right, we can show the slide now. So this is to show column 1, right? That is time is what? Column 1. Cases, column 2, right? Are we together? Beta is the first parameter. Gamma is the second parameter. And then for our initial condition, S naught is 762, I naught is 1, R naught is 0. And then now here I am defining the numerical solution. So the numerical solution here, I also want the output of this numerical solution to already be put in data frame. That's why I specify here as .data.frame. So this will put the outcome as a data frame, because originally the outcome, it will come out as a list, right? But I want to view it as data frame. So it will put it as, this one will help us to put it as data frame. And I told you yesterday that this ODE is a function in DE sub, and it requires for y, right? It requires you to put y times parms func, right? Is that okay? Now this h max is actually talking about the step, what's it called now? The step size, yes. So it's like you are specifying a step size for your numerical solution. All right. So when you do that, by out, you already have the results stored. When we did simulation, you know that we didn't have to put this line of code. Do you remember that there was nothing like this there? For simulation, did you see anything like this there? We just stopped at the previous line, isn't it? Because we are running simulation. But now we want to bring in data. And we have said we are using LSC. And what LSC does is to minimize the sum of square error, isn't it? So you have to bring in that LSC, which is what I have highlighted. The sum of square error, right? Do you see that? Sum of square error. But now, it's also important for us to know, by the virtue of the data we have in our hands, when you are collecting your data, Prof already told us that we should know what kind of data do you need? Prevalence data or incidence data. Are we together? Because that's very important to know what component of our model output are we going to draw. Are we together? Are we together? So the data you have in your hand is prevalence. Now, because it is prevalence, in our model, in our SIR and the rest of them model, the prevalence in SIR model is represented by the I component. The I variable there is representing prevalence. Don't forget you are saying that prevalence contains the old and new cases, right? All right. So I represent the prevalence there. Is that okay? Are we together? We'll see another one where we'll be talking about incidence, for instance. But prevalence first. I represent the prevalence. Is that okay? The infectious class represents the prevalence. Okay. So the output of that class is what I need. That means that is what corresponds to the data that was collected. The output, because so that tells us now that for a process-based model, there are different outputs that we can get from it, but we must know what output of that model corresponds to the data that we have in our hands. Do you understand? What parts of that output correspond to the data we have in our hands? I know we have prevalence in our hands, right? So, and I must be able to correspond the part of the model that represent prevalence. Is that okay? For instance, I cannot just say R. I can't say out R. And I cannot say out what? S. Is that okay? Do we get that? So for that purpose, I will not say. So that's why we are now saying that this is the component of the model, this out I, right? That correspond to the cases data that we have in our hand. So you see now that unlike the statistical model that just looks for a function, right, to fit, this one just builds a whole system and extracts the component of the system that corresponds to the data. Is that okay? So meaning that from a deterministic model, you can extract a whole lot. You can have many outputs. So here I'm just using one of them based on the data that we have in our hands. So out S is the part of the model that corresponds to the data cases that we have, the cases 1 data that we have. Is that okay? So now we are saying that the difference between these two, and then we square it and take the sum of it. So when you run this model, so what you have done necessarily is again to link the model and the data. Don't forget the general procedure that I mentioned. Bring in your data, specify your model, link your data and your model, then define the optimization algorithm. Is that okay? Are we together? So we have successfully linked our model and our data. So next thing is to fit the model. So we want to find the parameter values that minimizes the error function. So, and that process is called what? It's referred to as optimization. And so for us, we have many algorithms that is available in R, and one of them is the nether-mid algorithm, which is a default in the function optim. Optim is one of the base R function that come with your R. It helps to optimize. Is that okay? It's an optimization algorithm. Are we together? So how are we going to do it? This is it. Now optim requires basically 3 things. Now when I say basically, that means there are many other things that we can put there. But basically 3 things that must be there. One, the parameter you want to estimate, you have to specify an initial guess. Is that okay? You must specify an initial guess. Just like the other one we did yesterday. So you know we had to specify a start. And I told you that we'll mention how you can do that.